Well, thank you very much. I will. So I will talk about doubling constructions, and so some people might have already heard this talk, but I will give more details, and from time to time I'm asked some question proving that it's not easy to get a right feeling about this construction. So the idea is to do some construct new constant mean curvature surfaces or minimal surfaces starting from known one by perturbation arguments. So unfortunately, there are two types of ideas. So first of all, there is an idea which is a geometric idea that this object should exist or not. And then, since this is a perturbation argument, you can rephrase these ideas into a PDE framework, and you can read on some PDE exactly all the geometric features of the surface you are looking for. So this is this relation between the geometry and the PDE, which I would like to talk about. And at the heart of the construction is what is called Green's function. So don't be too afraid. There won't be much technicalities in PDE. It will be very simple. But you will see that in solving some linear PDE, then you can have a good idea about the construction which is possible or construction which are not possible. So this is, I will try to convince you that some constructions are possible and some constructions are not possible. Well, I'm not so sure this is clear, but so the general idea is the following. So you start with lambda, which is minimal surface, and which is compact oriented in and embedded in a 3-manifold. And the general idea is roughly the following. So I'm not very good at drawing pictures, but I imagine that this is lambda in the manifold. And what I do is that I will take two copies of lambda, separate them slightly. So imagine that you have one copy of lambda slightly above and one copy of lambda slightly below. I will make all this precise. And then what you would try to do is to perform a connected sum between the two copies of lambda. Okay, so here you take two copies of lambda. So for the time being, two copies of lambda, we don't know very much what it means. And then you separate them slightly, and you want to connect them by small necks. So, so basically, this is what you do if you have some, for example, your two fingers, and you have some oil in between your fingers, and you slightly open your fingers, and you will see that there is a small neck, which is, and this small neck is exactly the same neck you will have here. So the question is, how can you make this construction possible? As I explained, this is a perturbation argument. And one of the key tool is the Jacobi operator, which reads about lambda, which is the Laplacian on lambda, plus the square of the second fundamental form, and then the Ricci curvature enters, and capital N will be the normal unit normal vector about lambda. So this Jacobi operator arises in when you look at the minimal surface, lambda, and what you want to do is that you want to take a normal graph for the function phi over lambda. So you call the mean curvature of this normal graph, so which you call lambda phi. And then when you expand this, then you find that this is the mean curvature of lambda plus the Jacobi operator applied to phi. And then, so this is Taylor expansion in powers of phi. And then the next term is quadratic in phi. So it depends on the norm of phi squared. Okay, and the norm of phi you choose depends on the function space where you choose the function phi. Now, one important definition is you will say that lambda is non-degenerate if J lambda, the Jacobi operator, has trivial kernel. And one of the so if this is so, then the implicit function theorem tells you immediately that if you start with a surface lambda which is minimal, you can perturb it slightly and obtain constant mean curvature surfaces. So one can perturb lambda into a one-parameter family lambda epsilon for epsilon in some small interval, such that, well, lambda epsilon has mean curvature epsilon, and lambda epsilon is a graph over lambda for some function, is a normal graph over lambda for the function phi sub epsilon, which is given by epsilon psi plus something which is much smaller. Okay, so there is a power extension in powers of epsilon. And what this function psi solves is the equation J lambda psi is equal to 1. Okay, so this is very, very simple. And now the idea is that if you start with lambda here, then what you can do is that you can take somehow a copy of lambda which has been slightly moved. And so this is here, lambda sub epsilon, which has mean curvature epsilon. But also what you can consider is another surface which is below, and which will be called lambda minus epsilon, which has mean curvature minus epsilon. So here what is important to see is to understand what is the orientation of the surfaces you're working with. Okay, so this one has mean curvature minus epsilon. This one has mean curvature plus epsilon. And you see that it makes sense to try to connect these two leaves here by some neck, like this, and try to connect them. And try to make in such a way that the resulting surface will have mean curvature epsilon. So you see that the orientation fits. So here the orientation is this way, and here the orientation is the other way, but the mean curvature has the other sign. So this is what I will try to explain. So there is a result, and also telling you what you can do in this framework. And also, I would like to explain a bit what is going on here. And here, in fact, what you can do to perform this connected sum, what you can do is that you can insert here a small rescaled catenoid. So small rescaled catenoid. So the catenoid in Euclidean space is the surface of revolution which is generated by the Koch curve. And what is also possible to see is that this is a bigraph. Okay, so you can cut it in two halves. The upper half is a vertical graph, and the lower half is also a vertical graph, so for some function. And these functions are given by this. So you take y in R2 minus the unit ball, and you map it to, and the function is plus or minus log of y plus a constant C0 plus, in fact, something that decays quadratically as y tends to infinity. So this gives you the behavior of the end of the catenoid. So you see that if I'm not wrong, so you have to be careful about the signs. And the log of, so what it tells you is that up to a constant, then the ends of the catenoid behaves like the graph of the log function. So the plus models the upper hand, and the minus models the lower hand. Now, so what you can do is that you can rescale this catenoid by a factor eta, and what you have, so take eta to be positive small, and define x is eta times y. And then the rescale catenoid will have two parts like this, and it will be a bigraph. And what is important is to see what is the expansion of this bigraph, log of x plus c minus log of eta plus something which in fact eta squared mod x minus 2. Okay. So this expansion here will play a very important role in all the constructions I'm talking about. So now in what you can do is that this parameter epsilon is very small, so this size here is very small. And what you can do is that you can embed a piece of the catenoid here and try to do a connected sum of this leaf here and that leaf there using a piece of catenoid. And this is what we are going to understand. Now it turns out that I've not talked about Green's function, but I am. And so Green's function is Green's function is defined. We call it gamma. And it is defined as follows. So I'm choosing a point P on lambda, and I'm defining Green's function with the pole at P to be the solution of J lambda gamma is equal to minus 2 pi, a Dirac mass at the point P. So it is well known that since the lambda is non-degenerate, then what you can do is that you can find a solution. So Green's function does exist. And what is very important is the behavior of Green's function near the pole. And this is very well known. So the behavior of Green's function near the pole is exactly so close to P. So you can use geodesic normal coordinates close to P, and you find out that gamma of x can be expanded like minus the log of x plus, in fact, a constant. But what is important for us is the part that blows up. Now, so the idea is now you see that the leaves that have constant mean curvature epsilon or minus epsilon, basically up to this parameter here, up to this error here, they are the graph of the function epsilon times psi or minus epsilon times psi. So the idea is to consider the graph of epsilon psi minus eta gamma and minus epsilon psi plus eta gamma. So let me try to draw a picture. And so maybe I will use this picture here. So this is the graph of epsilon psi minus eta gamma. And here minus epsilon psi plus eta gamma. And so let's agree that the white curve, white surface is the graph of epsilon psi. And then when I plug this in, then I get something that looks like this, and here something that looks like this. And the point P is, roughly speaking, here. Okay, so the idea in those gluing construction is to match exactly the expansion of the graph here with the expansion I would have of the one of the rescale catenoid here. And so if you try to match these two expansions, what you get so on the one hand, you see that close to this, so here, you see that you have the graph of a function that can be expanded like epsilon psi of p plus eta log of mod x plus smaller terms. And if you look at the lower end, the upper end of the rescale catenoid here, you see that it has the expansion. So you want to match this with the expansion, which is eta log x plus eta c minus eta log eta plus smaller terms. So at a formal level, you see that, what do you see? Well, you see that here everything goes fine. And then basically what you want is that the constant here and the constant there are of the same size or even match. But you see that this term here is much larger than this one. So this one you can probably forget. And in first approximation, then you see that you have to choose the relation between epsilon and eta is given by this in first approximation. So once you have done exactly all this work, then you're in good shape. And what you can do is that you can use well, cut and paste. And what you can do is that you can form a surface which looks like the graph of epsilon psi minus eta gamma here. Here it will be close. It will be exactly the small catenoid you have inserted in. And here it will be the graph of minus epsilon psi plus eta gamma. So here what I will do is that I will draw the small catenoid here, and I will use cut and paste here to produce this surface. So this surface has almost the mean curvature equal to epsilon here. Also what it has is that almost the mean curvature is equal to epsilon there. And in fact here what happens is that the mean curvature is almost 0. It is not exactly 0. It is 0 when the catenoid is embedded in R3. But when you embed the catenoid, even if you do it in a nice way, then you have some mean curvature here. But in fact, the mean curvature is not so large. And the last step is to do a perturbation argument. To perturb this surface into a surface that has mean curvature epsilon to get a constant mean curvature surface. So here, this is where everything goes. This is where the details are absolutely terrible. So since I'm sure you don't want to hear them, I will put all the very complicated details below the carpet. And what I will do is that I will just tell you exactly what is the result. And you will see that there is somehow a new surprise. So there is a theorem that I obtained with Sun, which is you have to assume P is a non-degenerate critical point of the function psi, and further assume that psi of p is not 0. You see that this is important because otherwise, if psi of p is equal to 0, then this identity here runs into trouble. And then this surface I have cooked up here can be perturbed into a constant mean curvature surface whose mean curvature is epsilon. The surface can be perturbed into a constant mean curvature surface whose mean curvature is epsilon, and this is true for all epsilon small.
So it doesn't matter whether it's maximum psi?
It doesn't matter. So then the problem is that what you obtain might not be embedded, because you see that on my drawing psi does not change sign, but psi might change sign. But if the minimal surface you start with is stable, then in fact psi does not change sign, and then you can get embedded surfaces. Then it doesn't matter if it is a maximum or a minimum. But what is very weird is that the connection doesn't work if you're not at the critical point of the function psi. So from the geometric point of view, there is it is quite intuitive. From the PD point of view, it is extremely complicated to explain. But from the geometric point of view, you will see that you will immediately see that there is a problem if you try to connect, as is done in the drawing, at a point which is not a critical point of psi, then you see that you run into trouble. So let me draw a picture instead of doing some very complicated explanation. So basically, so this is the graph of epsilon times psi and minus epsilon times psi. And then what I do is that I perturb this by using Green's function. So you will see that this will. So if the point P were here, then that would basically, the idea is that this would create a surface which will remember that there is a slope here. And if you want to do the same job below, then you see that this is not completely true what I'm saying, but the idea is that eventually what you have is some kind of piece of catenoid here which is slightly bent. And unfortunately, if you have the catenoid in Euclidean space, the only way you can bend it is by bending the axis of the catenoid. So this means that the upper hand and the lower hand, they bend exactly in the opposite directions. And there is no way to bend the catenoid in such a way that this will bend this way and this will bend that way. Okay? But you see that, so you see that here, for geometric reasons, you seem to run into trouble. However, if you try to perform the connected sum here, well, you see that the graph of Green's function will look like this. The one below will look like that. And in fact, it looks much better to insert a catenoid here. So, so from the PD point of view, there is a good reason why the perturbation works in this case and doesn't work in that case. But I have no proof of the fact that the connected sum cannot be done. What I'm saying is that from the PD point of view, you see that you run into trouble, but I have no proof. Anyway, so this is a quite general result, but then usually people are working in spaces which are not as general as manifolds with arbitrary metrics. And for example, what you can do is try to do as an exercise, you can try to do exactly the same thing when I consider R2 mod out by 2 pi z square. Okay, so what I do is that I take a lattice, so I take this cross R as my manifold. And here, it is clear that I have a minimal surface to start with, because what I can do is that I can take a surface at constant height, and this is minimal. So unfortunately, what happens is that when you cook up the Jacobi operator about this surface here, you find out that this is the Laplacian on a torus, on a flat torus. And the Laplacian on a flat torus has a kernel, because the constant function belongs to the kernel. And so you cannot apply exactly the construction I have given you here. Instead, and the reason why you cannot apply the construction I have given you here is that you cannot cook up the Green's function at some point. Let's say this is 0 here. Okay, so the reason why you cannot do this is that if you integrate both sides by parts, here you find 0, and here you find minus 2 pi. So the idea here is to add this constant here. And now it is known that there exists a function gamma which solves this equation. And the reason is that if you average the right-hand side on the torus, then it has average 0, if I'm not mistaken, because the surface of the torus should be 4 pi square. And so this time, gamma does exist. And you can start exactly the construction I have outlined. But because of this, what you obtain is that if you cook up the mean curvature of the graph of epsilon times gamma, then what you find is that, well, it is the mean curvature of the site you started with, which is 0. And then what you start, the next term will be epsilon times j gamma, and then plus higher order terms. And you see here that what you get is epsilon divided by 2 pi plus higher order terms. So immediately you see that the graph of epsilon times gamma does not tend to produce a minimal surface, but already tends to produce a surface whose mean curvature is almost constant. And this one, you can then, starting from this, you can then insert the catenoid, and then you can do the perturbation, and everything goes well. You have to, in this, and what you get is are surfaces which have been found by Manuel Ritoré quite a long time ago. And, well, what they look like this. So these are doubly periodic, and if you extend them by periodicity, this gives you doubly periodic constant mean curvature surface, whose mean curvature is, in fact, quite small. So the mean curvature will be epsilon. And they are 2 pi periodic in both directions, or horizontal directions. But as I said, these surfaces were already found by Ritoré, by other methods. Now you can play exactly the same game in S2 cross R, starting from the leaf S2 cross 0, which is minimal. And then you can perform exactly the same connected sum as above. And this produce, starting from a minimal surface, this produce constant mean curvature surface whose mean curvature is very small. Now, another example is the great circle, the great sphere in S3. So this one is minimal, and here this time you can try to play exactly the same game. And but now the Jacobi operator here looks like Laplacian on S2 plus 1. And unfortunately, this one also has kernel, so you cannot apply directly the theorem here. But what you can do is the following. So the reason why it has kernel is, so if I picture S3 here, and if I picture here S2, the reason why it has kernel is because what you can do is that you can rotate the S2, which is here, and keep the mean curvature being 0. And so this produces Jacobi fields. And these Jacobi fields, in fact, are the coordinates functions on S2. And so the only thing you can do is the following. So instead of doing the connected sum at one point, you can try to do the connected sum at many points. So first of all, the parallel surface to S2 will have constant mean curvature, let's say epsilon, and the one which is there will have constant mean curvature minus epsilon. And what you can do is that you can try to connect them, but using the symmetries of the problem, what you are going to do is that you are going to put many points to which you will connect the surfaces. And basically what you can do is that you can arrange the catenoidal necks periodically. Excuse me. You can do it by taking 2 catenoidal necks, which are antipodal on, so 2 points on S2 here, one here and one there. So this point P and point Q. And perform the connected sum at those 2 points simultaneously. In fact, what I'm trying to tell you here is that you are going to use the symmetries of the problem and to get rid of the non-trivial kernel of this operator here. What? You get, what you get? Yeah.
No, you can't have a constant mean curvature sphere that's not.
That is not what?
Rotational sphere.
But it will be a rotational sphere. Oh no, the example you obtain here are rotational. So if you start in S2 cross R, you have a sphere which is very small, whose mean curvature is very big. And then when the mean curvature decreases, it becomes more and more like two spheres which are connected by a small neck. Two S2, excuse me, two S2 connected by a small neck.
That's a rotational sphere.
Oh, here you obtain, it's a connected sum. Yeah, it's a, yeah.
All the spheres in this are rotational.
But this one will be rotational. Yeah. You do the construction, imagine you have S2 here, right? With the, well, imagine that S2 is the plane with the metric of S2, and then you can do it rotationally. You take the point here. No? Okay. So here you can try to do it also, and the idea is that you can solve this equation minus 2 pi the Dirac mass at this point P, let's say this is the North Pole, plus a Dirac mass as the South Pole. So this equation here you can solve, but if I had only one point, the equation you would not be able to solve. And starting from this, then everything goes exactly the same, and you obtain this surface. But unfortunately, here there is also a lot of symmetries, and these surfaces can also be obtained by solving an ODE. So this is not very interesting to have such a complicated method to solve this problem. And what you get is a constant curvature torus, which are known by solving ODEs. The last thing I wanted to mention, last example, is the doubling of the Clifford torus, which was done by many people. So here you can take the Clifford torus in S3, which is S1 of radius 1 square root 2 times S1 1 over square root 2. And this time the Jacobi operator here as kernel, and this is twice Laplacian on the flat torus plus 2. And this torus is just T is just R2 mod out by 2 pi z square. I take two angles. Which are theta 1 and theta 2 to parameterize the two circles. And so this guy here has kernel. So you can see that if you take cosine theta 1 times cosine theta 2, for example, it is in the kernel of this operator here. So what you can do is, nevertheless, basically borrow the idea from here and perform a connected sum, not at one point, but at many points. And this was done by Adrian Butcher and myself. So theorem, my Butcher and myself. So the connected sum of two copies of the torus can be done at points of a lattice containing 2 pi z square and not included a regular lattice, not included in x plus minus y is equal to 0, well, theta 1, let's say. Theta 1 plus theta 2 equal to 0 mod 2 pi. So roughly speaking, what it tells you is that if you picture torus like this, 0 to pi, and if you take a lattice with enough points, okay, with enough points, then you can perform exactly the construction, the doubling construction, and doing connected sum at exactly those points. And what you get is a constant mean curvature surface with small mean curvature. And get CMC surface with small mean curvature for any value of the mean curvature, provided it is small. And, but basically, this is always the same construction. So now I'm going to talk about something which is slightly different. And this is a slightly more elaborate version of this, and which is due to Capouleas and Young. And the claim is that if you perform the connected sum at a lattice that has enough points, then in fact what you can obtain is not a constant mean curvature surface, but a minimal surface. So if the lattice contains a lot of points, then one can obtain a minimal surface by doubling construction, by doubling the Clifford torus. And I would like to try to convince you that you can read. So these surfaces were already obtained by you, I think, a long time ago. And but what I would like to convince you is that you can read somehow the existence of the surface by studying Green's function. So what I do is that I take this picture here, and I take points. So Pij will be the points of coordinates 2 pi over n times I, 2 pi over n times j. And n is a parameter. And what I do is that I want to cook up Green's function for this, for the Jacobi operator which I have there. Okay, so the factor 2 doesn't matter too much. So ij go from 0 to n minus 1, and you put Dirac masses at all the point Pij. Okay, so you have a lot of Dirac masses, and you can see that this function. So it is. So if you have a lot of points, then gamma does exist. There is no problem with this, and also it is. You can study the behavior of gamma at the punctures, and at the puncture it looks like the graph of log. So here there is nothing new, but in fact the problem is to study gamma as n tends to infinity. Study gamma as n tends to infinity, and we will see that as n tends to infinity, there is something special that comes out. So here, what you do is that first you define g by scaling by a factor n. And you find out that the function g, this time, solves Laplacian, flat Laplacian g plus 2 over n squared. G is equal. Now what I look is that I have expanded everything by a n, and so my lattice, the cell of the lattice are now where 2 pi over n and become 2 pi. And by periodicity, what I can do is that I can study this, in fact, in the torus, like this, pi minus pi here, so theta 1, theta 2, and in fact extended by periodicity. Okay, so what I'm looking for is a solution of this equation here that has 0 Neumann data. So on this square. So here there is a problem, in fact, and the problem is the following: as n tends to infinity, what happens is that this term here goes to 0. When this term here goes to 0, what happens is that it is less and less likely that the solution G does exist. Because if you remove this term here, then in fact, there is no solution of Laplacian G is equal to a Dirac mass on the right-hand side. So we expect that when n will tend to infinity, there will be something going on. So one of the piece of the function g will blow up. So the so in fact here you can almost I will tell you exactly what is going on, and the following is that the idea is that you can cook up the solution g in the following way. So first of all, you solve Laplacian g naught is equal to minus 2 pi Dirac mass at the origin plus 1 over 2 pi. And as we saw already, since you are on the torus here, then you can solve this equation here, and because the right hand side has mean 0, and you know exactly what is the behavior of g naught. And then the idea, because of this 2 over n squared here, the idea is to look for g of the following form. So here you will take a constant, c. Let me call the constant kappa. And then, well, c. C will be better for constant, but kappa can be a constant also. Plus the sum from j equals 0 to infinity. And here you put 2n squared to the power g, j times gj. Okay? And so if you plug this, if you look at this equation here, you plug this inside this, what you obtain is very simple. The equation here reduces to 1 over 2 pi plus 2 over n squared times c plus the sum j equal 1 to infinity 2 over n squared to the power j. And here I have Laplacian gj plus gj minus 1, okay, equals 0. So you can see that if you want this to be equal to 0, then it's not so complicated. So first of all, you can choose the constant c to be equal to minus n squared over 2 pi. And then you can solve inductively the equation Laplacian gj is equal to minus gj minus 1. And this has a solution because the right-hand side, you have to choose it in such a way that the average of these functions over the torus is equal to 0. And then you can prove that inductively you can solve these. So you see this gives you exactly the dependence. So this formula here will exactly give you the dependence of the function g in powers of n. And once you have this, then you can go back to gamma, and you find out that gamma has some special structure. And you find out that near any of the poles of gamma, let's say 0, gamma can be expanded as follows. So gamma of x is minus n squared over 2 pi minus log n minus log mod x plus other terms which are not so important. But what is very important here is that you find exactly this, which proves that there is a singularity at 0. And also here you find that there is this constant here, and this constant, in fact, has 2 terms, but the only interesting one is this one, that is behaving like minus n squared. And right, so now what we are going to do is the following. So I cannot draw a graph over the Clifford torus. So what I will do is that I will picture the Clifford torus like this. Okay, so that will be simpler for me. And then what I will do is that I will take the normal graph over the Clifford torus of gamma times factor, let's say, epsilon. So here what I will do, we'll have something like this. So this is the point 0, and this is the graph of minus epsilon gamma. And here below, I will draw the graph of epsilon gamma. So everything is periodic. So if you have a pole here, there is another one here. So it will look like this, and here probably like that, and so on. Okay? And what you do is that you try to insert here the catenoid, as we have done before. And you see what is extremely important is that here there is this factor which is very big. And so this gives you basically epsilon times this, when you change the sign, is basically the amount you push the torus in one direction. And then you put the log term. And so if you do the matching with the asymptotics of the upper end and lower end of the rescale catenoid, then you find out that you have to scale the catenoid by epsilon also. And you find out that there is a matching, as we have done before. And the matching comes from the different constants. And so remember that there was a constant also in the asymptotic expansion of the catenoid. And what you find out is that for the matching to be correct between the two expansions, the upper end, the catenoid, and the graph of minus epsilon gamma, and the other one here, there, then you find out that this 2 pi plus log epsilon has to be, roughly speaking, equal to minus epsilon log epsilon. Okay, so you can exactly remove this. And what it tells you, because it tells you that I have, excuse me, n. And what it tells you basically, because this one is much smaller than this one, it tells you that the number n over 2 pi, n squared over 2 pi, has to be of the size minus log epsilon. And so you see that here, what you have is that there is, in fact, you can take it exactly like this. Well, you can take epsilon to be exactly equal to exponential minus this. And because you can assume that this one is, you can neglect this one. And so what you see here is that there is a link between the number n and the parameter epsilon. So you're not free. You're not free to move the parameter exactly as you want. And basically, for each n large enough, you will get exactly one minimal surface. So, right. So if I have, if I have 2 more minutes. So basically, the key point in this construction can be really understood in the analysis of the behavior of Green's function as n tends to infinity, as the number of points tend to infinity. And you see that at the end, what you get is a relation between the parameter epsilon, which is the size of the small catenoid, and the number n, which gives you the size of the lattice. So, so this, you can use exactly the same idea to produce minimal surfaces with what is called free boundary minimal surfaces. In B3, in the unit 3 ball. So the idea is, I will just draw 2 pictures. So this is the unit 3 ball. And what I can do is, so what I'm looking for are minimal surfaces which are embedded inside B3, but they meet the boundary of the 3 ball orthogonally. So this is the meaning of this free boundary. So one possible solution is exactly the disk, the unit disk. And you see that it is minimal and meets the boundary orthogonally. And the idea is exactly to perform exactly the same construction. So you can slightly lift it and slightly take one below and try to do a connected sum. But this time, in fact, and you want to try to do a connected sum and get a minimal surface that meets the boundary orthogonally. And this time, the idea is to perform the connected sum between two copies of the unit disk. But you are going to perform the connected sum on the boundary. So if I were to look at this picture from above, then what I will see is, well, this was the unit disk. And now what I have done, I have inserted half catenoids, which are arranged periodically along the boundary, like this. And the result, and so they don't look very periodic on my picture, but they should be arranged periodically on the boundary. And the result is that you can play exactly the same game. And the result is that if the number of points is large enough on the boundary, then you can perturb the doubling construction into a minimal surface. And so this gives some kind of new construction to a result of Schoen and Fraser and Schoen. So they obtain exactly these surfaces by a very different method, and for not only for when the number of catenoid is very large, but for all number of catenoid larger than 2, I think, but also what you can do is that you can obtain a new surface also by plugging in the middle a catenoidal neck. So you can also perform a connected sum in the middle. And this one is new and can be obtained exactly using the same type of arguments. And this was obtained by Abigail and Tatiana Zolotareva and myself. But basically, the idea is exactly the same, and there is an analysis of Green's function to be done, and but the analysis is slightly more involved than this one, and then there are very bad, details which I will not mention, because when you deal with function spaces and so on, it becomes a bit technical. I would like to thank you for your attention.